Hi everyone, this is lesson 1.2.3, and in this lesson we're going to take a look at permutations with restrictions. Anytime we work with a problem that is a permutation problem with a restriction on it, we want to start by looking at the restriction. However, the mistake that we want to avoid is thinking that because there's a repeated object in a set, that imposes an external restriction to the problem. When there are repeated objects in a set, what we do first is determine the number of permutations of the entire set, and then we divide by the number of permutations of the groups of repeated objects. Thus, the number of permutations of the set AABBBC will be 6 factorial divided by 2 factorial for the 2 A's and 3 factorial for the 3 B's. Additionally, we want to make sure that we remember that the word AND means multiply and the word OR means add. Often in a problem, you can determine what operations to apply by simply talking through the scenario in your head and listening for your own use of the words and or in the description. For our first example, let's find the number of distinct permutations of all the letters in the word addition. Notice that there are 8 letters in the word with 2 D's and 2 I's. Thus the number of permutations will be 8 factorial divided by 2 factorial, 2 factorial, or 10,080. Now let's take a look at the distinct permutations of the letters in the word multiplication. Notice that there are 14 letters in the word with 2 L's, 2 T's, and 3 I's. And so the number of permutations will be 14 factorial divided by 2 factorial, 2 factorial, 3 factorial to give us an incredibly large number of permutations. Now we're going to start to work through problems that impose restrictions on the problem. But to start off with, we're going to look at all the number of ways that we can permute the letters in the word algorithm. And to start off with, we're going to say that there will be no restrictions here. In this case, the problem is pretty straightforward because there are 9 letters in the word and there's no repetition. So the answer is 9 factorial. Now let's see what happens when we impose the restriction that the first letter must be G. Remember that to answer this problem, we want to start with the restriction. And since there is only one G to choose from, we write a 1 to represent that choice. Now we need to permute the remaining letters. And because we need to start with a G and include the remaining letters, we will multiply our choices together. And so we get 1 times 8 factorial, which is 40,320. This following restriction is one that gets frequently tested. How many ways can we permute the letters in the word algorithm if the vowels and the consonants must be kept separate? The first thing we want to do is address the restriction. In this case, we're separating the vowels and the consonants. So let's take a look at this and notice that there are 3 vowels. And so there are 3 factorial ways that we can permute those 3 vowels. We notice that there is also 3 consonants. And as a result, there are 6 factorial ways of permuting the consonants. Notice that we put a multiplication in between these two because we need the vowels and the consonants to answer this problem. This product is not the final answer though, because there are 2 groups of letters that need to be permuted. It was not specified in the problem the vowels come first or second, and so there's some ambiguity there, and we need to take into account the fact that it could be in either order. We do this by multiplying by 2 factorial, the number of ways of permuting 2 groups, and our final answer is 8,640. Now let's take a look at the restriction that says that the letters A, L, G must be kept together. In this question, what isn't said is just as important as what is said. Notice that we didn't say that it had to be in the order A, L, G, just that the letters have to be together. And so that gives us a little bit more option in terms of how we put these together. And now there are 2 ways that we can finish this problem, and in both cases we have 3 letters that have to stay together. As always, the number of ways we can permute 3 objects, or 3 letters in this case, is 3 factorial. And then because we need to include all of the letters, we're going to multiply this by the number of ways of permuting not just the other 6 letters, but also this group of 3 letters. We're going to include this as its own unique, big letter. And so there were 7 objects that we're going to actually permute. And the product of 3 factorial and 7 factorial is 30,240. But this question could also be done By first permuting the small group, which will just give us 3 factorial, and, implying multiplication, permuting the other 6 letters that are left over, and then multiplying by the number of places that we could place that small group ALG in and amongst the other 6 letters. And in this case, because there are only 6 letters, there are 7 possible places that we could put that little group ALG. Since we only need to choose one place, we won't use 7 factorial, we'll just use 7, and our total product will be 30,240, just as it was before. And now let's take a look at the opposite restriction. The letters ALG must not be all together. And it's important that you do recognize that this is the opposite restriction, because that's actually the easiest way to answer this problem. So from earlier in this problem, we know that there are 9 factorial ways of permuting the letters in this word without restriction, and that there are 3 factorial, 7 factorial ways of permuting the letters with the ALG together. So now, to get the restriction where they're apart, we'll subtract the number of together restrictions from no restrictions to get 9 factorial minus 3 factorial, 7 factorial, which gives us 332,640 different permutations where the letters ALG are not together. Okay, now let's try a question where we're imposing restrictions on a word where there are repeated letters. First of all, we'll start with the no restrictions question mark. In this case, even though there's no restrictions, we still have to deal with the repetition of the letters. There are 6 letters total, so there are 6 factorial ways we can permute them, but we need to divide by the number of permutations of the 3 A's and the 2 N's. Now, what if the first 2 letters must be A? As before, we'll start with the restrictions, and we'll worry about the repetition of the letters in just a little bit here. Since there are 3 A's, we have 3 choices for the first letter. Once we've chosen that A, there are now 2 choices for the second letter. And then there are 4 factorial ways we can permute the remaining 4 letters. Now that we've dealt with the restriction, we need to remember about the repetition of the A's and the N's. So we'll divide by 3 factorial, 2 factorial. Now notice that this next restriction says that we're going to begin with exactly 2 A's. This is different from the previous one, which allowed for the possibility of there being 3 A's. It had to have 2, but it could have had 3 A's up front here. In this question, the restriction is actually on the first 3 letters because that third letter must not be an A. As before, we have 3 choices for the first letter and then 2 choices for the second letter. Now we need to choose a non-A letter for that third position, and there are 3 different choices for that. And now that we've dealt with the specific restriction, there are 3 letters left over that need to be permuted. And then finally we divide by the 3 factorial, 2 factorial for the repeated letters. Now let's determine the number of permutations of the letters in the word banana if the A's must all be kept together. Notice that this is just the together restriction that we've done before, with the added bit that there is some repetition of letters here. Since there are 3 A's, there are therefore 3 factorial ways we can permute the A's in that little group. And then the 3 other letters, together with the A's, make a group of 4 objects to permute. And then finally we have to divide by 3 factorial, 2 factorial once again, because of the repetition of the letters. Now for a different variation on the permutation theme here. In how many ways can we arrange 3 ping pong balls, 3 golf balls, and 4 tennis balls in a row? Now in a question like this, you really do have to assume that the balls of the same type are completely indistinguishable from each other. So we can tell just by a quick count that there are 10 balls in this problem, and thus there are 10 factorial ways of permuting that group. But because of the repetition of the balls here, we'll have to divide by the 3 factorial for the ping pong balls, 3 factorial for the golf balls, and 4 factorial for the tennis balls. Okay, another popular question that is a restriction of permutations is the one that requires us to alternate. Now in this case, how many ways can children be organized in a row where the genders alternate if, in the first case here, we're going to look at 6 boys and 6 girls. In placing these children in this row here, the very first decision we have to make is which gender we're going to start with. And since there are 2 choices, We'll start by just writing a 2. Then we have 6 choices for the first person of whatever gender we chose to go first, followed by a choice of 6 people for the gender that comes second. These products alternate and drop as we use up our options for each gender, giving us the following expansion. But notice that this product could be simplified down and written as 2 times 6 factorial 6 factorial. Now let's take a look at the same question. Let's take one of the boys away. Now we're only dealing with 5 boys and 6 girls. Now in this case, because there are more girls than boys, the girls must start this, so we don't have that same choice that we had in the previous question. We start by choosing one of the 6 girls, and then we choose one of the 5 boys. We now have 5 choices for the next girl. Then the products just alternate until we've used up all of our options, giving us the following product, which can be simplified by writing it as 6 factorial 5 factorial. Now let's take a look at a question about position. Alan and Barbara are 2 of 10 students on student council. There are 6 males and 4 females on the student council. How many ways can they line up? Let's say they're taking a picture, if Alan or Barbara must be the first in the lineup. Okay, because we know that Alan or Barbara must be the first 2 in this lineup, we get 2 choices for the first position. Then, because it doesn't really matter what order the rest of the group stands in, we'll simply multiply the choice of 2 for the first position, Alan or Barbara, by 9 factorial, the number of ways of permuting the rest of the group. Now let's change the question slightly. What if Alan and Barbara must be the first 2 people in the lineup? So it's not just one of them, they're both of them. Now, because we know Alan and Barbara must be the first 2 people in the lineup, this gives us 2 choices for the first position, and then only 1 choice for the second position, whoever's left over. After this, it doesn't really matter what order they stand in, and so there's 8 factorial ways of permuting the remaining students, and so we just add that to the end of our product. Now what if the question simply asks that a female student must be at the beginning of the lineup? Notice in this question that they're not referring to a specific female, just any female. And since there are 4 to choose from, we'll start with the number 4. After that decision is made, we really don't care what order the rest of the students line up in, and so we'll simply multiply this by 9 factorial, the number of ways for permuting the remaining 9 students. Now let's consider the question where the restriction is that we must have the same gender at either end of the lineup. In this particular question, you're not told which gender to start with. It's kind of up to us. And notice that this could happen in 2 different ways. We could, for example, start with the girls. There are 4 girls to choose from for the first position, which leaves us with 3 girls who could take up the last position. And then since we don't care about how the remaining group of 8 stand, we'll insert an 8 factorial in between these 2. Or we could have boys at either end, which is why we introduce the addition here. And then there are 6 boys to choose from for the first position, followed by 5 choices for a boy for the last position. And then because we don't care how the remaining students stand between those 2 boys, we'll insert an 8 factorial in between the 6 and the 5 to get our total number of permutations. The next question is being asked in the negative. How many ways can these students line up if neither Alan nor Barbara must be the first in the lineup? This particular restriction simply disallows 2 possible choices for the first position. So instead of starting with 10 choices, we start with 8 choices. Then, because we don't really care what order the remaining students stand in, we'll simply multiply by 9 factorial to give us our grand total for the number of permutations. Now let's revisit an old grouping question here. How many ways can these students line up if the females must all stand together? As we've seen in previous questions like this, there are 2 ways we could approach this problem. First, we could look at the girls as a single group of 4 and determine the number of permutations of this group, which will be 4 factorial. Then we consider the group of girls to be a single person or a single object. Together with the 6 males left over, that's a total of 7 objects or people to permute, and we'll write this as 4 factorial times 7 factorial for our grand total of 120,960 permutations. There is, however, as we've seen before, another way to do this problem. We still need to take note of the fact that there are 4 girls and that that little group of girls there needs to be permuted, and so that's going to be 4 factorial. Then we'll multiply by the number of ways of permuting the 6 boys that are left over, and that's going to be 6 factorial. Then notice that with 6 boys, there are 7 different places that that group of girls can be placed in and around the group of boys. And so we finish this problem by multiplying by 7. Once again, not 7 factorial, because we're just choosing one of the places to put the girls.